Hi, this is Lakshmikant Tiwari, and today I am going to start a brand new lesson on a machine learning. And the very first tutorial is linear regression machine learning crash course. So in this, I'll be doing a very deep analysis of a linear regression and how you can select the different kind of the features, how you can group the features based on the correlations to train it, and how you can improve the performance of your model. This is the one of the rarest in the rare tutorial series which you will find anywhere. This is going to be around a 2-hour long tutorial in which I'll cover almost everything about the regression, feature selection, normalization, learning curve, and the correlation of the features with the final labels, which is a house, the price of the house. So I'll start with the first linear regression introductions, then I'll tell you a little bit more about regressions and its usability, and then I'll talk about the linear regressions, the equations, and how you can assess the performance of the models, then when your model is going to be the overfit, then what is the bias and the variance trade-off, how you can decrease the errors with the help of the increasing the data size, and then what is the cost function, and then finally how you can decrease it. Once we done with the introduction of a linear regression, then we will start with the scikit-learn. Then I'll tell you about the scikit-learn, how you can utilize the scikit-learn into your machine learning journey, and what are the algorithms available into the machine learnings, how you can split the data, then how you can load the data, housing data sets, then you can do analysis of these data sets, then finally you can understand your data. And once you understood your data, then with the visualization you need to understand it a little bit more so that you can select a proper features to train your model. And then you can get the distribution plots for each of the features to understand it better, how it is correlated, then how it is correlated with the price, each of these features. And once it is done, then we can see it with the heat maps, how it is correlated. And then with the help of the correlated feature selections, with the help of this correlation matrix, we can do a feature selections, and then we can train our models. And once our model is trained, then we can assess the performance of our model based on the R2 score. And not only the R2 score, we will be also discussing about the mean absolute error, mean square error, root mean square error. And once it is done, then we will be making a function in which we will be storing all the informations together, so that later on we can analyze and we can compare the different features combinations and their performance together. And then we can do correlated features plotting with the regression line, and then we can do a feature selections with the different set of the feature correlations with the final label, which is price. Once it is done, then we can go ahead and learn more about the standardizations and the normalizations. And in the final piece of this tutorial, I'll show you how you can plot a learning curve. A learning curve will show you how, with the set data size is increasing, how your model is learning throughout its training and the testing. So this will be, there is so much to learn in this tutorial, and almost I'll cover everything. And in the comment box, please let me know if I have left out anything. And if you like this video, please thumbs up, and please do not forget to subscribe this channel. And let me know if you need any other help or any other tutorials on anything else. Okay, let's get started. Let us first understand what is linear regression. So here linear regression we are going to use for house prediction on a Boston housing dataset. Let's suppose that you are a real estate agent and you want to predict the house price. It would be great if you make some kind of automated system which predict price of house based on a various input, which is known as a feature. Supervised machine learning algorithm needs some data to train its model before making a prediction. That's mean here we are going to learn a supervised machine learning algorithm, which is a linear regression. So we'll be downloading a Boston dataset from a Seaborn library. Moreover, we can say we have a Boston dataset on which we will be working further in this tutorial. Linear regression is usually the first machine learning algorithm that every data scientist come across. And eventually this is our first tutorial in this series in which I am going to start a machine learning. It is simple model, but everyone needs to master it as it lays the foundation for other machine learning algorithms. Now the first questions can come in your mind that where you can use a linear regression, right? So you can say it is a very powerful techniques and can be used to understand the factors that influence the probability. It can be used to forecast sales in the coming months by analyzing the sales data for previous months. It can also be used to gain various insights about the customer behavior. Suppose that you have here the set of the data and it is spread across the y-axis, and now you want to fit a linear line there, so that you can also predict the y on given some x values. So the moreover, this is what we will be doing. We will be giving lots of the independent variable, which is the x here, and we will be finding out the variable y. So here y is a dependent variable. Y is dependent on a x. That's when you can say that here y is a function of x, right? So in our case, in housing pricing data set, the y will be a price of a house, and x would be other independent variables like number of rooms, square area size, and the how much house is old, etc. So those would be independent variable that comes into a x-axis. Let's go ahead and understand what is the linear regression. A linear regression can be, we can learn a linear regression into machine learning in a 3-step. The first step is data, which is the features derived from the data. Then we can feed features derived from the data to our model, a regression model. And then the regression model can learn from given x, and it can learn to predict the y. Then it can find out some kind of the relation in between x and the y. And once it found out the relation between x and the y, then it can predict y. Okay, and the y would be a continuous output, which you can also say a response to the input. Once it has that, then it can go ahead and let's see some example based on the regression. The first example comes in our mind is of course a housing data set, and another example comes in our mind is stock prediction. Since a stock prediction is also kind of the continuous variable, then it would come into a regression variable, regression classification, machine learning. Otherwise, it might have came into classification. Wherever a variable is continuous, we need to apply their regression. If a variable is distinct, it can be, let's say, if a variable can be classified into some kind of the category, then that will fall into classification. But if a variable is continuous, then it will be falling into a regression problem. So in stock prediction, we will be also doing stock price prediction, although in this tutorial we will be not doing this. In further tutorial we will do definitely a stock price prediction, and stock price predictions can be dependent on a recent history of stock prices, news events, related commodities, closing and the opening stocks, etc. Apart from that, there is another example like the tweet popularity. Let's suppose that how many people has retweeted your the tweet, and the dependent variables can be how many followers to you, and how many followers are there who has retweeted, and how many active followers to those who are following your the retweeted persons. Okay, that means you can say the total number of followers, and those kind of the features can be embedded as an input into a tweet popularity problem statement. So in this tutorial series, we will be working on predicting house price. That will be our case study, and you will be given a data set there, and in the data set we will be fitting a linear line based on the house size and number of rooms, number of bathrooms, kitchens, etc. And then we will be predicting a price of that house. Right? Perfect. Now let's go ahead and see how we can apply our linear regression on this. So there are two kind of linear regression. One is the multiple linear regression, and one is the, of course, just a simple linear regression. Okay, I'll take that ahead. Let's suppose that if we go with just single input linear regression, that's just a single variable. That's mean there would be just a single variable, and we will be fitting a single linear line so that it can find out total predicted price as close as possible. Okay, and once a linear line is fitted, then we can also find out that what is the goodness of the fit. That means how well your model will behave on unseen data. Your model can behave it can produce a good accuracy or good MSE and absolute error, etc. But it might not behave good on the unseen data. So we define a goodness of the fit on unseen data, and our goal is to minimize the total error, and the total error is mean square error or mean absolute error. Okay, so that can be minimized by using gradient descent algorithm. So what we do here, we found out we start fitting our line, and we calculate the mean square error, okay, with these fitted lines, and then we find out, and then we change our the line, and then finally we get our lowest error that with the gradient descent algorithm. Now you might ask a question, I have been talking a lot about the line. So what is this line? How you can represent this line? The equation is really very simple. There is y dependent variable for each of these data points. Okay, that's the yi for each of these data points, and then there is an intercept. That is the intercept. This is small value is an intercept, and then it found out that there is it calculates there is a slope coefficients. That's the beta 1. Then that is the slope. Okay, so this the angle of this line is a slope, and the xi is a data points of this x, that is the house sizes. Okay, so based on this we calculate the y. Okay, but once you get y, that is not always the true y. There is some error. Okay, and that is random error. That's where we introduce this error, a random error component. So our equation of this line becomes yi is equal to beta 0 plus beta 1 xi plus epsilon I. Okay, although in the further tutorial I'll be changing this beta 0 with the theta 0 and this one with the theta 1. Okay, so this is all we have been talking about a single variable linear regression, but there are some cases where we need to apply a multiple linear regression. Okay, in multiple linear regressions there could be multiple inputs, and apart from that there is a polynomial linear regression. Okay, so this is the this one is an input, this one is the example of also polynomial linear regression, and here this one is example of a multiple linear regression. So in this multiple linear regression, now we have included more than one input, that is the x1 and the x2. In x1 we have included the house size, and in the x2 we have included the number of bathroom. Okay, and based on this there is a plane fitting. Earlier we have been fitting a line here. Now we can see here there is a plane. Now we are fitting a plane there. Okay, and apart from that, even we can include a multi-dimensional data more than the x1, x2. Let's say we can also include the number of bedrooms, the total lot size, year built, etc. as an input to our model. That will become a multiple linear regression. Okay. Now after that, let's suppose that you have fit your model, you have built a great model. Now how would you assess the performance of your model? The technique is really fairly simple. Let's say once you have fitted a line or a plane, then you calculate their error, okay, with each of these the particular data points which is already given, and the difference between these we call it as a residual. Okay, and the line for which the error between the predicted values and the observed values is minimum is called the best line or the regression line. Okay, that is the regression line. And these errors are also called as the residuals, and the residuals can be visualized by the vertical lines from the observed data value to the regression lines. Now let's go ahead and see how do we determine the best fit of the line. Okay, we can fit a line which can just go ahead with these data points, right? So in that case it will minimize the error. Almost the error could be the 0, but that might not be the best model. Let's see how. In that case what happens, let's say you have a line, a very good line which has fitted very perfectly, but that could be a overfit. Okay, how it works, let's suppose that there is a model complexity. Okay, for this the model complexity is low, but for this model complexity is the very high, right? If your model complexity goes very high, then your model might get overfit to your data. So there is some trade-off between this. As your model complexity increases, your error might get decreased, right? So that is the training error. Your training error might get decreased, but after the some point your testing error might get increased, right? So we have to find out some particular the lowest point, or you can say a sweet spot where we can minimize our test error. Our goal should be minimize a test error, not a training error. The training error could be a 0, but this is not always the true that test error would be also a 0. Your training error could be the 0, but test error could be the very high. So this is always recommended that we should focus on a test error, and we can minimize the test error with some cost function, and we can minimize that cost function with the descent gradient algorithm, or you can say the gradient descent algorithm, right? As we increase our model complexity, there is some bias and the variance trade-off. If our model complexity is the low, then our bias will be low. Okay, sorry, our variance will be low. If our complexity is the low, variance will be low. That means complexity is the low, variance will be low. But here you see the variance is very high. That means your model is going up and down. Okay, very wiggly jiggly. But as the model complexity increases, your bias decreases, but your variance increases. So the moreover, you have to find out a sweet spot where bias and the variance meets together, and overall the testing error decreases. Ultimately you can say MSE, mean square error, decreases, and we just say that the mean square error is kind of the bias square plus variance. That means we have to find out some particular point where our mean and the bias fits together so that we can minimize our MSE on a test data set. Okay, now another approach to reduce the MSE mean square error or tackle the bias and the variance trade-off to increase the amount of the data, or to increase the total number of data points. Okay, so as we increase the total number of the data points, we find out that the error decreases. Okay, the true error decreases, and but after the some point what we found out that the true error and the training error meets at the same at some level. Okay, and after that it doesn't matter how much data points you increase or how much large data set you take, your error would be always the same. That's mean it is some kind of the limited by your models and the complexity of the models. Okay, so it's not always true that if you increase your data set to the infinity and you will get a zero error. That is not always the true. Okay, now let's go ahead and find out that how we determine the error. We need to make here some hypothesis, and one more thing I would like to change here, that I have just replaced here the beta 0 with the theta 0 and beta 1 with the theta 1. Okay, so the hypothesis is that let's say the h theta is our function, our output, which is eventually the y, which is a function of x, that is the feature. And then we have these two coefficients, which is intercept and the regression coefficients, which is ultimately known as the parameter. Our goal is to find out these parameters, and we can define the cost function j theta 0 and the theta 1 with this mean square error. Okay, so this is the mean square error, and our goal is to minimize the j of the theta 0 and the theta 1, that is the cost function. Okay, and that cost function, we can minimize that cost function with the gradient descent algorithm. Okay, we get some kind of this with the theta 0 and the theta 1, and our goal is to minimize it somewhere here. Okay, we can look it into another way with a more in a detailed way there. As you said there, yeah, as you see here, this could not be the always a minimum here. Okay, there could be a multiple minima, and you might get stuck into a local minima. If you go with this one, you might get stuck here, that is the local minima, but in this graph you will see here this is a global minima. Okay, so you might have seen while training your data set that sometimes you get a lowest error, but if you split your data in some other random state, you might get the accuracy something else. So that is how your gradient descent algorithm approaching, you might end up into a local minima. So this is also very important, how you split your training and the testing data set. Now it is time to implement this linear regression with the scikit-learn library. Scikit machine learning library, it is a package into a Python which has a lot of the already classical machine learning models built in its a package. Okay, so we use the scikit-learn library. It's simple and efficient tools for data mining and the data analysis. It is really very accessible to the everybody and reusable in various contexts. And moreover, the scikit-learn library is built on NumPy, SciPy, and the Matplotlib. And one more thing, you haven't seen my previous tutorials on the Matplotlib and the NumPy and the Pandas, you can go ahead on my channel KGP Talkie, and you can see there the data visualization, Seaborn libraries, Matplotlib, NumPy, and the Pandas tutorials there. Okay, and most of the important thing in the scikit-learn is that it is open source and the commercially usable with the BSD license. You can learn more about the scikit-learn at the scikit-learn.org there. And if you do not have the scikit-learn library, then you need to install your scikit-learn library. Okay, then you can click on the installation, and if you are using Anaconda, then you can run Anaconda install scikit-learn on your Anaconda prompt. Otherwise, if you are using a pip, then you can simply run here a pip install scikit-learn. Okay, so you can just copy it there, and you need to write here exclamation mark and then just paste it, and once you run it, it will install a scikit-learn library, scikit-learn package in your computer. Now let's go ahead and understand what are the algorithms are available into a scikit-learn package. Scikit-learn package have a lot of the algorithms in classifications, clustering, regressions, and the dimensionality reductions. In classification, it has the SVC, which is SVM, kernel approximations, SGD classifier, K-neighbors classifiers, naive-Bayes classifiers, linear SVC, etc. And in the clustering, it has the GMM, K-means, mini-batch K-means, VBGMM, etc. And in the regression, it has the linear regression, lasso, elastic net, ridge regressions, SVR, ensemble regressions, etc. So there are so many algorithms are already built into scikit-learn package. So you don't need to write each of these algorithms from scratch. And once we start working with the scikit-learn, we need to divide our dataset into the two part, which is known as the training and the testing. And apart from that, sometimes we also need to divide our dataset into the validation. The best guess to divide our dataset into 60% training and 15% validations and 25% testing. Otherwise, let's say if you don't have a validation dataset, then you can just go ahead with the 80% around the training datasets and 20% at testing. Or you can say the 75% the training datasets and 25% testing dataset. So how it works, it takes the training datasets and into the models, and with the help of the validation dataset, it tunes the hyperparameters, and then finally it do the predictions on the testing dataset. Right, now let's go ahead and start with the machine learning, machine learning with the regression problem. So we need to import the necessary packages here. Those necessary packages are the NumPy, Pandas, Seaborn, and Matplotlib. Let's go ahead. We need to write here import NumPy as NP, and then import Pandas as PD, and import Seaborn as SNS, and we are also going to import matplotlib.pyplot as PLT. Since we are working with the Jupyter notebook, we need to also run this command there, matplotlib as inline. Now we have these the package imported into our Jupyter notebook. Now let's go ahead import our packages from the scikit-learn library. So first we are going to load the Boston dataset. Let's go ahead load this from sklearn.datasets. Imports load Boston, and if you write here the load, you can see there are so many others datasets are already available in sklearn that you can also load. Okay, so let's go ahead and import the train and the test split from scikit-learn. sklearn.model selection, import train test split from sklearn.linear model. Now we are going to import our linear regression there. Now let's go ahead and import some metrics which we will be using to evaluate our model performance. From scikit-learn.metrics, import mean absolute error and then mean squared error. Okay, now you might be wondering that how do I know these things? Okay, how do I know that the load Boston is available into the sklearn.dataset? Okay, so let's copy this sklearn.model selection first and paste it into Google. Then you will see here into sklearn.model selection, right? So in this there is there is so many APIs are available which we can use. Like all these APIs in our the further lessons in the future we will be using. So these are the APIs which can be used into a model selection, and we have imported linear regression from here. From this model, from a model selection we have imported train and the test split. Okay, that is here, train and test split. And we can also import grid search CV with cross validation, parameter grid, parameter sampler, randomized search CV, etc., etc. Okay, and apart from that, there are so many other the APIs are available there. You can import. So let's go ahead and see in the pre-processing. We have this kind of the pre-processing there. In this lesson later on, I'll be importing their mean max scalar and standard scalar. Okay, this one. Okay, which will ultimately standardize our features by removing the mean and scaling to the unit variance. And apart from that, you can go ahead and you see here there are so many APIs are available which we can which we can import from there. Okay, so let's go ahead and further see here into the dataset. In the dataset, we have these kind of the datasets like load Bostons, breast cancers, diabetes, load digits, files, iris, etc. Okay, apart from those, we have here the clustering and the base class and utility functions, all those things, right? And similarly into the metrics, let's go ahead and search this matrix. In fact, we can search it here. Here we have a matrix. In the matrix, we have a scores, and we have a classification matrix like accuracy score and area under the curve, average precision curve, balanced accuracy score, variance score loss, and classification reports, etc. Right? So these are the metrics which we can use to evaluate our model, how good our model is performing. And there are some regression metrics like mean absolute errors, mean square error, mean square log error, median absolute error, R2 score, etc. R2 score is also coefficients of determinations. We will be using these R2 scores to determine the the goodness of the fit of our model. Now let's go ahead and load the Boston dataset. We can load this with the load Boston. Boston is equal to the load underscore Boston. Sorry, we need to run this one also. Now once we have run that one, now we have a Boston dataset imported into our Jupyter notebook. Let's go ahead and check our Boston dataset type. We can check that with the type of the Boston, that it says that this is a bunch of the data. Now let's go ahead and check the keys of the Boston's dataset. What are the keys available into this Boston dataset? And the keys of this Boston dataset is the data, target, feature names, descriptions, and the file names. Okay, and apart from that, let's go ahead and check this with the Boston dot DSCR. Okay, so the .DSCR provides you the description of this data set, although this description is really very complicated. So I have already written this description in very nice format. Let me copy this and paste it here. Let's go ahead and paste it here. If you see here, we have this. Sorry, let's make it into raw. So here we have this Boston dataset description there, and this description says that here. Okay, you see here, I think I already have there. Okay, no problem. So this dataset says that this project comes from the UCI machine learning repository. The data was collected in 1978, and each of the 506 entries represents aggregate information about 14 features of the homes from various suburbs located into the Boston. and these are the features. Let's go ahead and see the features of the Boston dataset, and then we can get it with by typing here the feature names. So these are the feature names. CRIM, that is the crime. This is the per capita crime rate by the town. JN, this is the proportion of the residential land zoned for the lots larger than the 25,000 square feet. Indus, this is the proportion of the non-retail business acre per town. Here CHAS, this is the Charles River dummy variable. NOx, this is the nitric oxide concentration. RM is average number of rooms per dwelling. Age is the owner occupied units built prior to 1940, and DIS is the weighted distances to 5 Boston employment centers, that is the distance. RAD, this is the index of accessibility to radial highways, that is the how easy to get the highway. And tax is the full value property tax rate for $10,000, and PT ratio is the pupil teacher ratio by the town, and B is it is calculated as the 1,000, where BK is the proportion of people of the African American descent by town. LS stat, this is the percentage lower status of the population. If LS stat is larger, that means the lower status of the population of the lower status is larger. And MEDV is the median value of the owner occupied home in $1,000. Okay, that's the MEDV. But you see here there is no MEDV, which is actually MEDV is mean to get the target variable. Okay, that's the Boston dot target. This is the the MEDV. So what we will be doing that based on these the features, based on these features we will be predicting this target. So we need to first train our model on some set of the data, and then finally we will be testing our data, we will be testing our model, and we will be finding out the parameter, the metrics or the accuracy, you can say that how good model is based on the our predicted value on the testing data. Okay, now let's go ahead and found out that now let's go ahead and get the data into our the Boston data into the data. So what we can do here, the data is equal to the Boston dot data, and once we have the data, let's go ahead and check the type of the data. There now you can see here the data is the NumPy array there, and let's go ahead and check the shape of the data. The shape of the data says that the 506 rows and the 13 column. That's mean there are 13 features. If you count these features, there would be 13 features and 1 target variables, and it says that the 506 entries there. Okay, that is the number of rows. Now let's go ahead and make this data into into a pandas data frame that we can make here with the data is equal to pd dot data frame, and then data is equal to the data, and then columns is equal to Boston dot feature names, and then here we have data dot head. There now you can see there one thing you might have noticed here, that there is no price column here. Okay, because the price column lies into the Boston dot target, so we'll be including the price column here. So let's go ahead include the price column into the data. Okay, so here we have a data price is equal to Boston dot target, and then we can say here the data dot head. Now we have here our price, so we'll be predicting this price based on these features. Okay, so these 13 features. Now let's go ahead and understand your data. scikit-learn package becomes really very handy when we come to the understanding our data sets and training our model. So let's go ahead and understand our data set there. So with the data dot describe, we can understand our data. So here for each of the columns we have got the total count. So here every the column has the same number of values, that is the 506 rows, and the mean of these columns are given there, standard deviations of these columns, and there we can also get the minimum the minimum of these the columns, and we have also the maximum of each of these columns, and then here first quartile values, and then the 50%, and here is a third quartile, that is the 75% of the data. So in a crime, 75% of the data is less than 3.6, and in the zone 75% data is less than 12.5. Okay, now let's go ahead and see it in another way, that is with the info. Okay, so the data.info, if we run that on a pandas data frame, then you will see there it has every column has 506 values, and the types of each of these columns is a float. Okay, and here you can say here how much memory it is taking into your computer. I'm sorry. Let's go ahead. Now let's go ahead and check if your data set is having any null values into the data. Then you can check the null value in your data with the is null. So you can say here the data dot is null. Then it will say there the true and the false value. Then you can just simply apply there the sum, and it will say that the crime is 0, zone is 0, index is 0, almost everything is 0. That's when there is no null value into your Boston dataset. Okay, now let's go ahead and start working with the visualization of your dataset. The visualization will make you understand your dataset, and it will help you to choose the right features to fit in your model. We will start by creating a scatter plot matrix that will allow us to visualize the pairwise relationships and correlations between the different features. It is also quite useful to have a quick overview of how the data is distributed and whether it contains the outliers or not. So let's go ahead and plot a pair plot with the help of the Seaborn library, a Seaborn package there. So let's go ahead. The sns.pairplot, it will find out that it will make a kind of the matrix there for each the column. So one column versus the another column, and then finally it will plot the scatter plot into the pair grid. Since the data set is quite large and total number of feature is 13, and there is one price column, so it's a kind of the 14 cross 14 matrix, and the 14 cross 14 pair grids, it's quite huge. Even though in this you can see there, if you compare there the price here, okay, you can find out that there is some relation, and that relation is ls stat there. Okay, and apart from that you will find that there is here a relation, and that is the RM. Okay, that is the total number of rooms in your house. Okay, and there is some kind of relation is also here. Okay, that is the ZM. Okay, so similarly you can find out that these are some kind of the relation, and if you want to explore these relations in a correlation manner, okay, then what we can do there, we can plot a correlation matrix. So in the correlation matrix we can also find out that there what is the correlation of each of these columns with the price. Higher correlation shows that there is high chance of the predictability based on that features to the price. But before the correlation, we are going to plot a distribution plot for each of these the distribution plot, that's mean for each of these features. So let's go ahead and see the distribution plot. Now the one question you might ask, that why the distribution plot before a correlation matrix? Because if your feature is not well distributed, then it might not help you to predict your the target variable, right? So in this case, the price of your house. That means if these features are not if these features are not distributed logically, then then it might not help you to predict the price. How you can see here, this is well distributed, and you can see there is the negative correlation. But if you see here, this is highly concentrated at some point. That means this feature will not help you much to find out the price of the house. And similarly, you will see these three features. These three features are highly concentrated, or you can say skewed. These features are skewed, and if these features are skewed, then these features are not definitely gonna help you to predict the price of your house. And ultimately, these features will increase the complexity of your model, and that will decrease the accuracy or R2 score, or the the accuracy metrics into a testing data set. Now let's go ahead and plot these distribution, okay, for each of these features. So there are total 14 columns, including price as well. So let's go ahead and implement first distribution plot. There I'm gonna implement it into the 2 rows, and total columns is gonna be a 7. That's mean I'm going to here plot 2 by 7 columns, a kind of a distribution plot for each of the rows, each of the columns, to understand better the distribution of the features, or a distribution of the data. So let's go ahead and first create a subplots into matplotlib there with the plt. So here we have plt.subplots, and there we have total n rows. There, sorry, total n rows, we have rows there, and here we have n columns. There we have columns, and then here we have a fixed size, and here we are going to give a fixed size of 16 cross 4. Let's go ahead and run this. Once we run this, you will see here a axis, right? So there are the 2 by 7 axes are there. Now I am going to plot a distribution plot for each of these columns there, so that we can look closely and we can find out that which features are skewed and which features we can intelligently select to fit our into a model. Okay, now one more thing you can see here, these grids and the axes are overlapping to each other, and if you want to remove those overlaps, you can just simply write here the plt.tight layout. Now you can see there these are kind of well behaved 2 cross 7 grid layout. Now let's go ahead and implement our distribution plot. So here I'm gonna first get total columns there. Okay, the columns, that is call into our data columns, it will return the total number of columns there. Total columns, actually a string of a list of the columns there, the 14 columns. And let's go ahead and set here the index is equal to the 0. Now I'm going to run it with the for loop there. I have a for I in range of rows there. So this for loop will run into rows there, and another for loop will run into columns. Now we have for loop for rows and for loop for column as well. Now let's go ahead and plot a distribution plot. Here we have a dist plot. Now if you press shift and the double tap, you will see here the type of the parameter which we can pass into a distribution plot there. We need to pass here our data, and we need to also pass here the axis on which we need to plot this, that is the AX. Okay, this is the AX. Now let's go ahead and pass the data there. The data is equal to, or you can just simply write, well, yes, the data. And here the data we need to pass for a column. So let's go ahead and pass a column. So the column provides a list of the features, and we are going to select the first features that we can select with the index. So we have got here first features, and then we are going to provide here an axis ax. The ax is equal to I, and here a j, right? And now I'm going to increase the index is equal to the index plus 1. Now let's go ahead and plot this. Now you will see here a very beautiful plot there. A plot, now you can see here these plots are really very skewed, and crime, JN, CHAS, CHAS, B, these are not really good to include into our feature. Okay, so the plots which are good to include into our feature is RM, which is normally distributed, as well as here you can get the PT ratio, or the tax, the DIS, these LT stats. So these are the quite good. Okay, so these two are the quite good to include into our prediction. Why? If distribution is a normal distribution, then there is very high chance of the correlation with the target variable. And if your feature is highly skewed, then these features are not gonna give you much information to predict your final price. Okay, so finally you can remove these features which are highly skewed. Now this is the visual way to find out that which feature is gonna be fit to find out our final feature selection to predict the final target. Okay, so this is the way, in a visual way, to select a total of feature. So you can say a feature selection. Okay, now I'm going to show you how you can select a feature with the help of the correlation. Now I'm going to write a correlation matrix. I'm going to plot a correlation matrix, and it's a plot there. Then in that you can see there these skewed features would not be much correlated with the final price. Let's go ahead and create a correlation matrix that you can do with the core. Okay, so here we have a corrmat is equal to the data dot core. Now if you plot here the corrmat, you will see here the correlation matrix. So with this correlation matrix, if you see here, let's find out this one, crime, right? So you see here the crime is just correlated is 3.8, okay, sorry, 0.38 with the price. Okay, and now let's go ahead and see the RM. Okay, here you see the RM. The RM is very much correlated, that is the 0.69. And if you see here this LS stat, L stat, okay, so LS stat, you see here LS stat is also very much correlated, although this correlation, negative correlation, says that if LS stat increases, the value of price will decrease, which you can get from here as well. Okay, this is the distribution plot of the L stat, but here you can see here if L stat is increasing, then the price value, the price is decreasing there. Okay, right. Now apart from that, what we can get here, let's go ahead and plot here the matrix there, the correlation matrix. Okay, so here I'm gonna plot this correlation matrix into kind of a heat map that we can do with the help of the heat map, Seaborn heat map function. So let's go ahead and first get a fig, and ax is equal to plt dot subplots, and then here we have a fig size is equal to 18 and 10. There, this kind of the fig size we have. Now let's go ahead and plot this with the heat map, sns dot heat map. I'm gonna pass here correlation matrix data, and I'm also gonna say here annotate it. So the annotation is equal to the true, and then I'm gonna say here the annote keyword is equal to it takes the dictionary. So there it takes a size, font, etc. You can set from here. So I'm gonna set here font size is equal to the 12. Now you will see here it is very, the pretty much a nice graph there. In the price, it's very visible. L stat is pretty much correlated with the price, and here you see another one is let me see, where is another one? RM, yes, here is RM. RM is also pretty much correlated, that is the 0.7 correlation. So here it has positive correlation. So the positive correlation says that if RM increases, the price of house will increase. Okay, so apart from this price, the correlation, there is also lots of other correlation. So these correlation says that if these two features are highly correlated, that means there is multi-collinearity of these features. Let's say here NOx and the DIS is highly correlated. Okay, highly correlated, minus 0.77. That means there is multi-collinearity. If your two features are highly correlated to each other, okay, then these features are not gonna including these both features together into prediction is not gonna put you the information. I'll be taking another series on the feature selections. That will be a very good series in which I'll be talking about a lot about the multi-collinearity and the feature selection and the feature engineering. But for time being, you need to just understand if these two features are highly correlated, then it is not always good practice to include both features. The good practice is include to only one feature, and also include only those features which features are correlated with your target variable. So here target variable is a price. Let's say if I ask you to include this charge variable, okay, the charge feature. The charge feature is just 0.18. So it is not investing, much information. It is not putting enough information to predict the price. So ultimately, if you include the charge into your model selection, that is gonna be just increase your model complexity and decrease your accuracy. Okay. Now let's go ahead and create a function by which we can select a correlated features which is highly correlated with the price. I'm not going to remove those features which are highly correlated to each other. Otherwise, this tutorial will be too long. So I'm just going to get those features which are correlated with the target variable. Okay. In the future, I'll be making other videos in which I'll be also find out the multi-collinearity. But for time being, let's go ahead and find out only those features which are correlated with the target variable, which is a price in our case. So let's go ahead and write a function, a method you can say in a Python, the def correlated get correlated feature, and in this I'm gonna pass here core data and threshold. Okay, so the threshold will define here that for how much threshold we are going to get the data. Let's suppose that if we define 0.7 for 0.7 threshold, so in that case, in the 0.7 thresholds, I'm gonna get here L stat and RM. Okay, although RM is kind of 0.69, so I'm not going. We will be not getting RM actually. We will be getting only L stat. Okay, so I'm going to just write that functions which are correlated with the target variable. Okay, so let's go ahead, make a empty list there, a feature list, and then the value. So the value will say that what is the correlation value, and now I'm going to write here a for loop there. So I and then index in, and I'm also going to enumerate their core data. Let's go ahead and enumerate the core data index. Okay, so you see here the core data index. What is the core data index? If you want to get the core data index, you can get that from here. sorry, yes. So here we have a Corrmat. Actually we have a Corrmat, index. So these are the Corrmat index, and if you write here the values, then you will get the values of these core index. Okay, so these are the values. So I'm going to enumerate to these the values: crime, ZN, etc., etc. So let's go ahead and find out here if absolute value. Okay, so if absolute value is greater than threshold. Okay, so if ABS of core data, and then in that I'm gonna pass here the index. The index will be, let's say, the first column. Okay, that would be the crime there. And if this index, okay, the core data index, absolute value of this is greater than threshold, then I'm going to include into our feature. So it's a feature dot append, then index, and index is a column. Okay, and here value dot append, and in this I'm going to append the value of the correlation. Okay, now let's go ahead and create a data frame there. So here I'm going to create a data frame with the PD dot data frame. Then I'm gonna say here data is equal to value, and then I'm going to also say here the index is equal to feature, and then columns is equal to core value. And let's go ahead and return from this function. Now I have written here df. Okay, now let me show you a sample. Okay, how the df will be returned there. So let's define here a threshold first. Now I'm going to define here threshold 0.50, and I'm going to say here core value. The core value is get correlated feature. That's mean now it will return that the correlated features. Okay, and here we have a Corrmat, and we are passing here a price there, and then here we have a threshold there. Okay, right, perfect. Now let's go ahead and print here core value. Now you can see here there is a correlation value, and this correlation value is defining their correlation value. It has selected actually these features which have a correlation more than 50, 0.50. Okay, and those features are RM, PT ratio, L stat with the price. Okay, and their correlation value is 0.69 and -50 and -73. Okay, so this is the intelligent way to select your features before fitting your model. Otherwise you might fit your model with all the features, but you might not get a good accuracy. So this is, I would always recommend you to select your features intelligently. Otherwise you would end up making your model too complex, and it will finally overfit, and it will give you a very low training error but very high testing error. Okay, now let's go ahead and get the data only to these features. Okay, RM, PT ratio, L stats, and the price. So that we can get with the correlated data is equal to, here we have a data, our original data, and I'm going to get here, let me show you here first what is the core value dot index dot values. Now you see here, so we are going to just select these features. Okay, So 3 features and 1 final target variable from core value, then dot index. Now we have correlated data. So let's go ahead and see our correlated data's first 5 rows. So in the first 5 rows we have, and here there are 3 features and final predictor value, that is the price there. So this is our target variable. Okay, now let's go ahead and now plot a pair plot, okay, and correlated matrix for this. So let's go ahead and plot first pair plot in between these features and target variable. So here we have SNS dot pair plot and correlated data and PLT dot title layout. Now let's go ahead and see this. Now you can see it very intelligently there. Here we have a price. Now you can see here L stat is fitting there. The PT ratio, although it is not giving you pretty much not giving you the much linear relation, but somehow it is giving some information to the predict the price. And you can also see the distribution of this PT ratio is also good. It's not skewed, although this is not a perfect normal distribution, but still it's not skewed. And then you can also see here the RM. In RM you can see definitely there is a linear trend. There is more number of RM, it's gonna be predict a high number of a larger price there. Okay, so this is the pair plot. Let's go ahead and see the correlation heat map there with the SNS dot heat map with the correlated data dot core, and here I am gonna also note it true, and in note keyword I'm gonna pass here in a dictionary there, and the size of the text is 12. Let's go ahead and run this cell. Now you can see here, okay, each of these are highly correlated to each other. Okay, the price is highly correlated with the L stat. The PT ratio is correlated, more than 50% correlations, and total number of room is also highly correlated with the price. Although one thing you can see here, the L stat and the RM is correlated with the 60% together. So in this lesson I'm not gonna show you how you can remove the multicollinearity in the features. In further lessons I'll definitely teach how you can remove a multicollinearity, but for this tutorial let's go ahead with this feature set. Okay, so what I'm going to do, I'm going to fit our model with these selected features. So the first I'm going to shuffle and then finally going to split the data. Let's go ahead and first get a x. X is our feature vector there with the correlated matrix, with the correlated data. So if the correlated data have the price column as well, so I'm gonna first drop here price column, and price column is on axis 1. Otherwise if you don't write axis 1 it will throw an error. And then y is equal to correlated data, and then we have here price. Okay, now you can see here x dot head. Now x is our feature vector and y is our target, right? So let's go ahead and train test split our x, that is the feature vector. So x underscore train here, x underscore test, and then we have y underscore train, and then finally y underscore test is equal to train test split. And in the train test split I'm gonna pass x, y, and then test size here. The test size is equal to 0.2. The test size is 0.2, and then I'm gonna pass here a random state is equal to 0. So if you also pass a random state is equal to the 0, you will get exactly the same kind of the data is split. In that case, we will be getting almost same kind of the accuracy. So let's go ahead and run this. One thing you might have noticed that I have written here a capital X but here a small y. This is because the capital X I have written, it is a general the convention in machine learning, the people that and this also represents that there is a vector, okay, and it's multiple column. That's why I have represented it X, capital X underscore train. Although you are free to use whatever convention you want to use. Now let's go ahead and see the shape of X train and the X test. So here we have X train and X test. Sorry, X train and the X test we have, but let's go ahead and check the shape of this. Here you see here X train size is 404 samples and test samples size is 102. Okay, now let's go ahead and very quickly train our model. Okay, so the model is equal to linear regression and model dot fit is equal to X underscore train, Y underscore train. This will the fit our model. It has trained our model. Now let's go ahead and do a prediction. Okay, so here Y predict is equal to model dot predict X underscore test, right? So here we have got a Y predict. One thing you might have noticed here is that the training and the testing of this model has been done in just 3 lines of code. I have made here a model, linear regression, then I had a fit a model, and then finally I had predicted it. So that is the beauty of a scikit-learn package. Scikit-learn package do every bit of the complex things behind the scene. You do not need to worry much about your model. It automatically train your model and it do the predictions, etc. Only you need to select your feature intelligently. Okay, once you select your feature very intelligently, then your model fitting is definitely gonna be give you a best result. Now let's suppose that you have trained your model and you have predicted your target variable. So what? How would you ensure that your predictions and the true value are matching to each other? To do that, we can see here our Y predict and Y test together. Although it's not completely pretty much visible, one more thing what we can do there. So here we have Y predicts and Y test together. Although let's go ahead and make a data frame. Okay, so here a df is equal to pd dot data frame, and in the data I'm going to just pass here, yeah, the data is equal to Y underscore predict and then Y test. Let's go ahead and check this df, right? Let's transpose this. Now you will see here. Okay, so if true value, that's the predicted value here. Let me just interchange this together. Okay, so here we have the true value there, and sorry, somehow it has Yes, now you can see here it has given you particularly, it has predicted 27, although the true value was 22. It has again predicted 22, true value was 50. Then it has predicted 26, but true value was 23. Okay, so this is how it predicts the house. It makes a house prediction based on the our trained model. And one more thing you need to understand, that we have trained our model only on these three features. And if you remember earlier, we had total 13 features. We had not included 10 features which are not much correlated with the price. Okay, now let's go ahead and see how we can evaluate our the performance of the model. Okay, now we are going to evaluate the performance of our model with the help of R2 score. Okay, so the R2 score, the value of the R2 ranges from 0 to 1, which captures the percentage of a squared correlation between the predicted and actual values of a target variable. A model with an R2 of 0 always fails to predict the target variable. That means if R2 is low, that means very bad model. If R2 is equal to the 1, that means the perfect model. It has predicted with 100% accuracy. Any values in between 0 and the 1 will indicate that the percentage of the target variable, that's when there is a high correlation between the predicted and the true target values. And a model which shows a negative R2 value, that means this is a bad model. Okay, the no better than some random model. Okay, you can get R2 score from sklearn.metrics, then you can import that R2 score. And apart from that, here is a mathematical formula of R2 score, although you don't need to implement this into coding, since sklearn automatically do these mathematics things behind the scene. So the moreover, this is the way how we calculate the R2 score. And if you see it into a graphical way, if R2 score is low, that's mean a bad model. If R2 score is good, that's mean if R2 score is equal to the 1, that's mean a good model or nearby 1. This is how we calculate the R2 score. R2 is equal to 1 minus square error, mean square error of this fitted line, and then absolute mean square error of this parallel line. Okay, that's the mean. Here you see there the mean. SST, that is the yi, the predicted value, the true value minus mean, and then here is true value minus the predicted value by square. Okay, now let's go ahead and see other regression evaluation metrics. Those metrics are mean absolute error, that is the MAE, and another metrics is mean squared error, that is the MAC, and the another one is the root mean square error. Okay, so the MAE is the easiest to understand because it's average error. MAC is more popular than the MAE because MAC punishes the larger error, which tends to be useful in the real world, and RMAC is even more popular than the MAC because RMAC is interpretable in the Y units. Okay, now let's go ahead and import R2 score and see how we can calculate these parameters. Okay, so here we are going to first import R2 score from sklearn metrics. Now we are going to calculate here a score. Score is equal to R2 score. Then we need to pass here test and y predict. That is the R2 score. Here we have a mean absolute error, MAE. MAE is the mean absolute error there, and in the mean absolute error we need to pass y test and y underscore predict, and then MAC is equal to mean square error there, and here we have y test underscore y predict. Right, let's go ahead and print this here we have here R2 score. Oops. Mean absolute error, that's the MAE. Now we have here MAC. Let's run this. Now you will see here in our 3 previous pages on which we had trained our data, we can find out that from here. So we had these 3 features on which we had trained our model. So this is R2 score. If we train our model with these 3 features, I have got R2 score 0.48 and the PT ratio, the mean absolute error is 4.4 and mean square error is 4.1. Okay, sorry, the 41. Okay, perfect. Now let's go ahead and store these features, store these performance features into Pandas data frame. Now let me tell you why do we need to store these features. Because now I'm going to select a few other features and then finally I'll make a comparison, and to make a comparison we should have our history. Okay, and in that case we will be needing R2 score, MAE and MSE to compare if we select, let's say, 1 features, 2 features, 3 features, 4, 5 or 13 features. So we will calculate based on those what is the our best which feature combination is gonna produce a best accuracy. So based on that you can finally write your model. Now let's go ahead and write a function to store the features. So we are going to store the total features here. Okay, so in the total features we have here a list in which I'll store a total features which we are using to train our model, and then we have here a total features name. Okay, and then we have here selected correlation value. That's mean earlier we had selected the 50%. I'll be also showing you that this is the 50%, this is 60%, this is 70%. So in that way you can make a comparison to your model that the way you are increasing or decreasing the correlation, how the total number of features are varying, and how scores, R2 scores, MAE and MSEs are varying. Okay, and I'm gonna also write here R2 score. I'm going to make here an empty list for R2 score, and for MAE value a empty list, and for MSE value we have also empty list. Okay, now let's go ahead and write a function or a Python method to calculate a performance matrix. Now once again, why a Python methods or a Python function? Because we will be using this many times and we are going to program it into a modular way so that we don't need to rewrite the code every times. That's why I'm going to write here a performance matrix method in which we will be just passing a 2 parameters and it will be giving you all the performance matrix parameters automatically. So let's go ahead, def performance matrix. There we have a features, the threshold which we are selecting, then we have here y true, and then here we have y pred. Okay, in the score we are going to store here R2 score and in the R2 score we are going to pass here y true and y pred. And similarly we have here MAE is equal to mean absolute error. Sorry, in mean absolute error we are also going to pass here y true and then y pred. And similarly in the MSE we are going to pass here mean squared error. In that we are also going to pass here y true and y pred. So once we have this, let's go ahead and get the total features, and we are going to get those total features. Okay, so here in the total features we are going to append the total features which on which we are training our model. That's the total features dot append, and length of features which we will be passing to this function, since it will be including the price which is not a feature. That's why I'm going to just -1 there. And then here we have a total underscore feature name. Okay, in this I'm going to append the total features which we are using there. Sorry, this should be a features. And here we have selected correlation value. In that I'm going to append that is just a TH threshold. Then here I have R2 scores. Okay, sorry, here we have R2 scores. So in R2 scores I'm gonna use here append, and in the append I have a score there, and then we have here MAE value. In the MAE value I'm gonna append here MAE, and then here in MSE value I'm gonna append here MSE. So once we have here MAE, once we have here R2 score, mean absolute error and mean square error, now I'm going to create here a pandas data frame for a better visualization of each of these performance metrics. So let's go ahead and give a name. Metrics data frame is equal to pd dot data frame is equal to, here we have the list, and in the list we are going to pass here the total features. And sorry, the first I'm gonna pass here total feature name, and then the total features, and after that I'm gonna pass here selected correlation value, and then I'm gonna pass here R2 scores, and then I'm gonna pass here MAE value, and finally I'm gonna pass here MSE values. Okay, once we have this, let's return this data frame from these methods, and we are going to return this into a transposed way. So let's run this, and now the time to get performance metrics based on our this y predicted and y test. So let's go ahead and run here the performance metrics. Here we have if you press here shift and the tab, you will see here we need to pass here features, thresholds, y true and the y pred, and the features, total number of features which we have selected to train our model. So these are the feature list. So let's go ahead and pass those feature list, that is into a correlated data dot columns and dot values, and the threshold, which threshold we had selected into the correlation matrix to select these features. If you remember, that threshold was the 0.5. Okay, and then here we have y test, and then we have here y predict. Sorry, here we have y predict. Now let's go ahead, run this. Once you run this, it says that there is error somewhere it says that the list object is not callable. Let me see how why it is saying that. This should be the right. Here we have y true and the y pred. Well, error was a little confusion into the other libraries, R2 score. So I have just sorted out that was in my computer. So you don't need to worry about that. The program is right. So now let's run this. Now once we run this, we see here what happens. Oh, it is showing that 2 lines. Then we need to rerun from here itself. During the testing, I had rerun it. Okay, now you see here, we have got pretty nice here. So in this, what we get here, we have the total features there, RM, PT ratio, L stats and the price. Then it says that there is total number of 3 features, the 3 features which we had selected, and the correlation condition was 0.5 and R2 score is 0.488 and mean absolute error was 4.4 and mean squared error is 41.67. Now you see here we are missing here a column name. So let's go ahead and fit a column name here. Okay. To set a column name, what we are going to do here, we are going to pass here a list of the columns. Okay. So we are going to say here columns. Columns is equal to the total feature name. Okay. So here we can say the features name, the total features, and then we can say here core values, that's the correlated values. Then we can say here what is the R2 score, and then we can say here what is ME, and then finally we can say what is the MSE. So let's rerun this from here. This says that there is somewhere invalid syntax. Let's go ahead and see which is in which one is the, sorry, this should be the not column, this should be the index. Okay, so still it's saying that yes, there I have to apply that. Now let's go ahead and see here. Now you can see here it's a pretty good there. Here is the feature names which we had selected to train our model. The total number of feature is 3. Correlated value, the condition which we had selected is 0.5. R2 score for this is 0.488. MAE is 4.4. MSE is 4.1. Okay. Now let's go ahead and see a regression plot of the features correlated with the house prices. If you have watched my Seaborn tutorial, in that I had shown you that how you can plot a regression plot without even running a regression algorithms. So let's go ahead and plot a regression plot using a Seaborn, and I'll be doing a regression plot RM versus price, PT ratio versus price, L stat versus price, and of course price versus price. That means for each of these features versus the target variables. So let's go ahead as usual, write code there, methods. So here we have a 2 by 2 matrix there. The rows is equal to the true and calls, that's the column. Now here we have a column is equal to the true. Okay, and here we have a pick and AX is equal to the PLT dot subplots, and in this subplots we have number of rows is equal to rows, and n columns is equal to calls, and we have here a pick size, and pick size is 16 cross 4, and here we have a call is equal to correlated data dot columns, index is equal to 0. Now let's go ahead run a for loop for 2 by 2 matrix. That's mean we need to run here 2 for loop there for I in range rows, and then for j in range calls. SNS dot reg plot is equal to the correlated data, and then here we have an index. So here what I'm going to do here, I'm going to pass the correlated data column index. That's mean it's going to get first RM, then PT ratio, then L stat, and then price, versus y is equal to the correlated data, that's the price. That's mean it will be always the one column versus price, and the AX is equal to AX, I, and J. Index is equal to index plus 1. Here we have a fig dot type underscore layout. Now let's go ahead and run this. Now you can see here very clearly we have here a price. Okay, we have here a price. As RM is increasing, price is increasing, so this is a linear fit. Okay, and as L stat is increasing, the price of the house is decreasing, and similarly as a PT ratio is increasing, a price of house is increasing, as price of house is decreasing. So this is how, without fitting a model of your model, you can plot a regression plot using with the help of a Seaborn regression plot library. Okay, so this is now we have been a lot discussing about the feature correlations with the more than 50%, which we had seen earlier. Let me show you from where we had started the feature selection. From here, the 50%. Now let's go ahead and see if we select only 2 features. That means those features which are correlated with more than 60%. In that case, only these RM and the L stat will be selected. Then what will happen if we select more than 60%? Okay, will these the accuracy metrics will improve or not? That's mean these things. Okay, and that's where this performance metrics function or a method is going to help us. We don't need to rewrite these codes again and again once we change the correlation value or a number of features. Okay, so this is the kind of the techniques of the modular programming, where you need to just write a single time of the code and then you call it again and again. Okay, now let's go ahead and select your features, only those features which are correlated with the price, I mean the target variable, with the more than 60% correlated value. Okay, so let's go ahead and see here a Corrmat there. There we have a price. Now you see here a 60% is L stats and RM. Only these 2 features are correlated with more than 60%. Let's go ahead and do that. So we need to put here threshold is equal to 0.60, and then core value, we have a core value is equal to get correlated features. I'm sure you might have remembered that we had written this get correlated feature methods to get the total number of features which are correlated above than the threshold. So here we are going to pass here Corrmat with the price. That's mean we are going to pass these correlated values, and then I'm gonna pass here a threshold. It will return the core values. Okay, the columns which are correlated with more than 60%, and those columns are RM and LSTATs, and there is correlation values with the price. Now let's go ahead and extract the data with only these two features and one target variables. So here we have a correlated data is equal to data and then core values dot index, and once we are done with that, then we can see it into with the help of the head first 5 rows of a correlated data. So here we have got these two columns, that's these two features. Now we are going to fit our model based on these two features. Okay, now let's go ahead and do one more thing. We have been doing the fitting of the model with the help of let me show you these lines of the code, like building a model and then predicting the model. So what I'm going to do here, I'm going to write here a function, a method which will do automatically everything. Okay, so let's write a method here. Def is equal to get y predict core data. So here I'll be just passing a correlated data. That's mean I'll pass this correlation data and then it will automatically do the predictions, since it includes here a target variable as well. So inside it will automatically train test split, it will do the train test split, and it will build the model, and then finally it will train it, predict it, and then it will return the predicted y variables. Okay, so this is very good techniques if you are testing your model for multiple times with different set of the features and with different set of the correlated values. This is going to help you a lot in your futures when you are building your careers in a data scientist field. Let's go ahead and get a feature vectors with the core data. Here we have a core data dot drop. Here we need to drop our labels, that is price, and which is located into axis is equal to 1. And apart from that, we need to get the y, that is the target variable, the core data. Okay, so here we have let's implement this with underscore, that's the convention here. The core data, we have here a core data, and there we have a price. Okay, so we have got x and the y feature vectors and label. Now let's go ahead, train test split it. Here we have x underscore test, y underscore train, y underscore test, and now it has a train test split, then it has x y test size is equal to 0.2, and then it has random state is equal to 0, and then finally we have model is equal to linear regression, and then model dot fit. You can see here the model fitting is just 3 line of code. The model dot fit, here we have x train and y train, and now let's get y predict. The y predict is model dot predict based on x test. Now I'm gonna return our y predict. Okay, so this function is going to help us a lot. We will be calling this y predict so many times. There we need to just pass a consolidated data which includes label as well along with the features. Then it will automatically do a train test splits, and it will build a model, train it, and it will finally predict, and once it is predicted it will return a predicted values. Now let's go ahead and get y predict there. Here we get y predict is equal to, with our newly written function get y predict, there we need to just pass a correlated data, this data, which will automatically get these the feature vectors and then labels. Once it is done, we have got the Y predict. Now let's go ahead and get a performance matrix for this. To get a performance matrix, if you remember, we have already written the codes for performance matrix. Now for this, we can pass here a correlated data dot columns. That's mean here we are passing a number of features which it includes, dot columns, and then values, and then finally we are passing here threshold. That's mean for which thresholds we have selected our correlated values. Then here we are passing Y test, and then finally we are passing here Y predict. Now you see here, this is the beauty. Now you can see here, we had selected a 3 feature earlier. We had R2 score 0.488, but here we had just selected a 2 feature. That's when the model complexity was reduced here in this case, and R2 score increased to 54. Okay, 0.54. So now with this you can see and understand it in a better way that it's not always good to include a lot of the features in your model. Even a reduced number of features can give you a better accuracy. Okay, now let's go ahead and see if we train our model with more than 70% correlated features. Okay, so let's go ahead and first see our correlated matrix. You see here, with more than the 70%, there we have only L stats and others are less than 70% correlated. In this case, we are going to, that means we are going to just select a single feature, that is the L stat. Now we are going to remove RM, and then we are going to see what is the R2 score for only single column. So let's go ahead and write here a threshold. Now our coding speed will increase since we have written most of the functions, only we need to call those methods here. Let's go ahead, write here threshold is equal to 0.70, and then core value is equal to get correlated features, and then we have here Corrmat. Then we have Corrmat price, and then here we have a threshold, and then here we have a core value. Okay, so let's go ahead and see here we have just selected L stat since only this is the column which satisfy the condition. L stat is the only column which is the correlated with price with more than 73%. Now let's go ahead and get your correlated data. Here we can get the correlated data is equal to, correlated data is equal to the data, and then core value dot index, and then here we have correlated data dot head. Okay, you see here we have got our the first feature, that is L stats, and then final price. Now let's go ahead and get Y predicts and do a performance matrix on this. It's really very simple. So we can do with Y predict is equal to get Y predicts, and there we need to just pass here correlated data, and let's call the performance matrix as well. In the performance matrix we need to pass here correlated data dot columns dot values, and then we need to pass here threshold, and then we need to pass here Y test and Y underscore predict. Let's go ahead and run this. Now you can see here we have included just L stat there, and in case of a single feature selection, correlated value was more than 70%, but R2 score is decreases to 43%. Okay, that is just 0.43. And in this case, ME and MSE has been also increased as comparison to the previous case. In previous case, we had selected the two features RM and L stat. So with these two rows, we can compare that if we remove RM, our R2 score has been decreased. Now let's go ahead and select only RM and see if we select only RM, then what happens? What would be the R2 score, MAE and the MSE? To do that, we need to get our correlated data. Correlated data is equal to data. Okay. In that we need RM and we need a price here. Okay. Perfect. Now we have got our correlated data, which includes only RM features and a price. You can see this with the head of appendage function. We have here now a single column, that is the RM. So that's mean this is going to be a single feature linear regression. Now let's go ahead and do Y predict. Now you can see how handy our methods have been, okay, which we had written. Get Y predict. In that we are going to pass here a correlated data, and then here a performance metrics. A performance metrics is going to be a correlated data dot columns and then dot values. Once we have that one, then we can go ahead with the thresholds and Y test, and then finally Y predict. Okay, now let's go ahead and run this. Now you can see here, even in case of the RM, it has been just a 0.42. Okay, so that's how if we had included RM and L stats together, its R2 score was increased to 54%, and if we include PT ratio in this, then this becomes the R2 score was reduced to 0.48%. Now let's go ahead and select all the features which are correlated with more than 40%. Okay, so that is also a very simple. In that case, what we can do, we can just copy and paste these codes. Here we have just 40%, and once we have that one, we can get here correlated data as well. And apart from that, we can get here performance metrics. See, this is how handy. Let's go ahead and run this. Now we get this one. There are so many features, 1, 2, 3, 4, 5, 6 features which are correlated with more than 40%. Let's go ahead and see our correlated data. So these are the columns of feature vectors which has been included into our new data set. Now let's go ahead and get up. With the performance metrics, you can see how beneficial it has been for us. We can select different features grouping together, and then we can finally find out the R2 scores, and based on this we can decide that which feature combination is going to be best for our model. Now let's go ahead and understand a little bit more about the normalization and standardization. One more thing I would like to tell you, that the model which we have been training here, that it automatically do the normalization, but still I'm gonna discuss a little about the standardization and the normalization. Why we need standardization and the normalization of the data? Because as you see here, there are many columns or features, and their features values are too much high and low. In case of the tags, these values are too much high, and RM values are pretty much low. So what happens during the fitting, regression coefficients gives better weightage to the tags and the less weightage to the RM. But this should not happen. All these coefficients should be on in a single scale. That's why we need to do the normalization and standardizations. Okay, by this curve, by this graph, as you can see here, that if you have some kind of the data set which mean is, let's say, some 10 and standard deviation is the 30, and if you scale it down to make it mean is equal to the 0 and the standard deviation is equal to the 1, then in that case we can say that our data has been standardized. Okay, that's mean the Gaussian mean will be the 0 and unit variance. Okay, and apart from that, the normalization is the process of scaling individual samples to have a unit norm. This process can be useful if you plan to use a quadratic form such as dot products or any other kernel to quantify the similarity of any pair of samples. The moreover, there are so many the normalization techniques are available into sklearn.preprocessing the API. In sklearn.preprocessing API, you can see here standard scalar, mean max scalar, max absolute scalar, robust scalars. There are so many other kind of the scalars. But by default, linear regression uses standard scalar. I'll show you how. Okay, so let's go ahead and make a model here. Okay, the model is equal to model is equal to linear regression, and apart from this, let me show you from somewhere where we have our X train and the X test. We might have here. Now you see here we have fit our model X dot fit with the X train and the Y train, and it says that okay, by default the normalize is false. But what we can do, we can also set a y this normalization is equal to the true. Then in that case it will do all the normalizations automatically. Okay, that would be is equal to the 1. That's mean if we copy this, okay, and if we copy this and paste it there, that it will be the true. Otherwise what we can do here, we can retest it here. Okay, we can retest it here. Otherwise let me see here if I can copy it and paste it there. Let me see here. Okay, we were working here. Let's go ahead and paste that. Now here we have our regression. The normalize is false. Now let's make it equal to the true. Now in this case normalize is equal to the true. Now let's go ahead and make a prediction. Here we have made a prediction with y predict there. Okay, and now let's go ahead and get a R2 score for this. Okay, now you remember this R2 score. Here we have R2 score there, y underscore test there, and then y underscore predict. So here we get R2 score for this normal with the normalization is 0.488, okay, which is approximately 0.49. So this is how you can do standardization and normalization. Now let's go ahead and find out the other combination. I think with the 40% we have already done. Let me see. Yes, with the 40% we are already done. So let's remove this. Okay, we don't need. Now let's go ahead and see how we can define a performance matrix. Okay, so okay, the performance matrix we have already defined. Let's go ahead and the performance matrix we have already seen here. The performance matrix, how our models are performing for different the set of the data. Now let's go ahead and see how we can get a learning curve. That's mean how our model is learning throughout this training and the testing. Okay, to do that, what we can do, I'm going to get here the learning curve and the shuffle split API from sklearn model selection. Okay, so let's go ahead and get that, so that we can get from the sklearn dot model selection, and then we can import it there, then we have here a learning curve. Okay, now we have got here a learning curve. Now let's go ahead and write a code for learning the plotting a learning curve. Okay, so here I already have a written code there, so I'm just going to copy this code there and paste it here, then I'll explain you how it is working. So here I have created a Python methods. This Python methods is taking an input estimator, a title, x, y limits, cross validations, number of jobs, that's mean how many cores I want to train, with how many cores on my computer I want to train my model, and train size. This train size says that 0.1 to 1, that's mean it will start from 0.1, that's mean the 10% of the data set, and then it will go to the 100% of the data set, that is the 1, and it will divide it into the 10 parts from 0.1 to 10, that's mean it will divide your data from 10%, 20, 30, 40, 50%, like that. Then here a traditional plt.figure format plot lib, then here I am setting just a title, x and the y labels. Then finally here a learning curve API. If you press here shift and the double tap, you will get a detailed documentation for a learning curve. It takes a lot of the inputs parameter as estimators, x, y, groups, train sizes, supples, scoring, etc. and etc. Okay, so in this case, what we are going to pass it here, estimator. Ultimately we will pass here a linear regression, x and the y, here feature vectors and the labels, cross validations, a number of jobs here, that's mean for how many cores we want to train our model, and here a train size. Okay, and this train size we are getting it at 10 times. And then finally here we have the train score mean, train score standard deviation. We get actually this everything into train size, train scores and the test scores. And then we are going to get the mean and the standard deviations of the train and the test scores. Once we have got that, then we are going to plot it into a grid format, and in the grid format, then this fill between what it does, it fills, it kind of creates a shaded area between the learning curves. I'll show you. Okay, and then finally this is plotting our learning curve. Here you see here train score mean and here test score mean. So these two lines are plotting a learning curve and these two lines are plotting a shaded area. Okay, and then finally the legends are being set at the best area. Now let's go ahead and get our feature vector x and the y. There we have got a feature vector x and the y, correlated data. We have dropped here label price on axis 1, and then we have got here label into y. Now let's go ahead and set a title here. The title is learning curve linear regression, and here I am also going to show the total number of features which I have selected for this. Now let's go ahead and paste the final piece of the code here. A shuffle split will shuffle it and then put a 20% data for validations and other data for training of the data set. And here the estimator which I'm going to pass a linear regression, and then I'm going to pass it into a plot learning curve methods, which is here. Okay, and once we have passed it here with all these parameters, here I'm going to pass here -1. -1 says that use all the available core on your computer just to run this cell. This says that the shuffle split is not defined, so we need to define that shuffle split here. Let's go ahead and run this. Now once we run this, since it has 10 folds of the data, that's why it has taken a little time. Now you can see here, this is what I was talking about, the shaded area. So with this piece of code, with these two lines of the code, you see here the red and the green. So the green is for cross validation and the red is for the training score. This says that how our training example changes. 407 examples were there. It took the 10%, 20%, 30, 40, 50% of the data sets to find out the total scores. So this is the learning curve, how it is improving your overall the model. Okay, perfect. So this is all about in this lesson. It has been almost the 2 hours while taking this linear regression machine learning crash course. Thank you so much for being with me, and thank you so much for watching this video. And please do not forget to subscribe this channel so that you can get updates directly into your inbox whenever I make a new videos. Bye bye. Have a nice day.